insulin secretion into the blood, that's only part of the story. So now you know how glucose concentrations stimulate this. So let's look at, okay, so we've got glucose in the blood. That's cool. What are we going to do with it? Well, I'm going to draw you two different cells and show you two different mechanisms, because one of them is the insulin-dependent cell, and most of your cells are insulin-dependent. Brain cells are not, but most of your other cells are. The other cell that I want to look at is a liver cell. And the liver has a different mechanism that we're going to examine because the liver has a different function when it comes to glucose. In fact, glucose is stored in the liver in the form of glycogen. So we have to figure out how that's going to happen. First, what is going to be present on any insulin-dependent cell? What do you think this thing is that I am just drawing here? It's an insulin receptor. So you have to have a receptor in order for insulin to have its effect. So the insulin receptor, the cells must be sensitive to insulin indicated by the presence of a receptor. Okay, so you assume that insulin comes in. Let's do the insulin-dependent normal cell first. Insulin comes in, and let's just call it good. We are just going to have a second messenger cascade that will take place. And this is, a common, insulin is a peptide hormone. This is a common mechanism for a peptide hormone. So the second messenger cascade culminates in something that, again, we've seen this before. Inside your cells are, can't remember what color I made it last time, vesicles that contain transporters. And in this case, the transporters are glut. You've seen this before. Vesicles inside a cell that contain transporters. Remember when we talked about ADH? That had water pores, aquaporins inside the vesicles, inside your collecting duct cells. Well, guess what this second messenger cascade is going to cause? It's going to cause the exocytosis of these vesicles, which inserts glut into the cell membrane. Glut doesn't just hang out there. Glut is there so that then a glucose molecule, that says glucose, can come and diffuse in. The cell, down its concentration gradient because we just inserted a glut molecule. Once glucose is in the cell can go ahead and metabolize it or do whatever it needs to do. Once the insulin goes away, the glucose concentrations go back down, the gluts are going to be endocytosed and removed from the cell membrane. And if you think about that, that's probably good because we certainly don't want to lose glucose from the cell. We don't want it to go the other way. And glut transporters will allow glucose to go down any concentration gradient, doesn't matter which direction. The liver is different because the liver requires us to store the glucose. So glut transporters are chronically in liver cells, always. They're always there. Here, the glut transporters are temporary. In the liver, they're always there. Insulin comes in and binds, and it stimulates I guess we're going to keep this color. We're going to show that glucose is going to come in. Insulin binding allows glucose to be turned into something different. It turns into glucose 6-phosphate. Glucose 6-phosphate, the important thing is that it turns into something else. This maintains a concentration gradient. No matter what is going on in the blood, you're going to have glut transporters in the liver cells that are available to absorb glucose no matter what, and we can continue to absorb it because we turn it into glucose 6-phosphate and we store it in the form of glycogen. And glycogen is where we can gather up as much glucose as we can and keep it for as long as possible. Now, hopefully, you're thinking, that's awesome, we got glucose out of the blood. What happens when your blood glucose levels drop? How does your body deal with that? Because obviously, insulin is going to decrease blood glucose concentrations. So there's got to be someone else coming into the mix. Lo and behold, someone else is. We're talking about them next.